Ang salitang thermal will always relate to heat at alam din natin ang epekto ng pagbabago ng temperature sa bodies. Maaari itong mag-expand or mag-contract. Ngunit kailan ba nagaganap ang thermal stress? Sapat ba na sabihing it is the stress due to change in temperature? Sa halimbawang ito na ang temperature deformation ay libreng mag-deform, walang internal force na pumipigil sa deformation na ito and therefore walang induced stress dito. What if hindi natin i-permit ang pag-deform niya by putting wall on the other side? In this case, yung pag-deform through change in temperature ay i-resist ng wall na ito. As it exerts the reaction force, doon din naman nagkakaroon ng internal force sa material natin dahil napipigilan yung pag-expand niya. So dito lamang magkakaroon ng tinatawag na thermal stress. Tandaan, if temperature deformation is permitted to occur freely, walang thermal stress. Pero once na hindi permitted ang deformation or may pumipigil dito, tsaka nagkakaroon ng thermal stress. And also, in temperature rise, there is material expansion. Sa temperature drop, merong material contraction. Ngayon, paano ba natin conceptually masusukat ang temperature deformation? Ang amount of linear deformation due to change in temperature o sa symbol na delta sub T ay ine-express sa formula na delta sub T is equal to alpha times L times the change in temperature. Ang alpha ay ang coefficient of linear expansion. Sa metric units, meter per meter degree Celsius ito at inch per inch degree Fahrenheit naman sa English units. Unique ito sa bawat material. Ang variable L ay ang length ng specimen at delta T ang change in temperature. Ito ay final temperature minus the initial temperature. Madali na itong gamitin kung free naman ang deformation. Pero ang critical dito ay ang paghanap ng loads or stress na dulot ng temperature deformation kapag prevented ito. Subukan natin sa problem na ito. A steel rod 2.5 meters long is secured between two walls. If the load on the rod is 0 at 20 degrees Celsius, compute the stress when the temperature drops to negative 20 degrees Celsius. The cross-sectional area of the rod is 1200 square millimeters. And the coefficient of linear expansion equals 11.7 micrometers over meters times degrees Celsius. And E equals 200 gigapascals. Solve assuming A, that the walls are rigid, and B, that the walls spring together a total distance of 0.500 millimeters as the temperature drops. Given this data, we are asked to compute the stress o thermal stress. Sa mga problems na isosolve natin, ang key is to imagine or again, assume. First thing na pansinin natin is the given temperature. Ito ay temperature drop, kaya ang tendency ay lumiit ang steel rod. So paano pagaganahin si imagination? Sa case na ito, imagine na disconnected ang rod na to sa wall. E di patuloy lang ito naliliit. Para ibalik ang rod na ito sa original position, attached sa wall, kailangan natin ng axial load P para magkaroon ng axial deformation due to that load at mai-connect siya sa wall. Through this, we can say na equal dapat ang deformation due to drop in temperature sa deformation due to axial load input. Ito ang equation ng temperature deformation. Ito naman ang deformation through axial loads. Simplify P over A to stress and we get this. Canceling length L, we now have the formula for stress sigma. Stress is equal to E times alpha times delta T. Using this formula, let's substitute our given. Meron tayong change in temperature from 20 degrees to negative 20. And also, let's insert the coefficient of linear expansion. That will yield a stress of 93.6 megapascals. Take note na ang lumabas na thermal stress formula, walang length. Ibig sabihin, thermal stress is independent to length. That's our answer for A. Pero umextra pa si B na sinabing paano naman kung may movement ang walls natin kapag nagdadrop ang temperature. They spring together daw. So naglalapit sila for a total distance of 0.5 millimeters. So ganun din ang case. Anong load dapat ang magbabalik sa wall na ito sa position niya? Again, yung yield na ito ay given as 0.5 millimeters. So ang total deformation due to temperature drop ay equal talaga dapat sa deformation due to force para sa steel rod plus sa movement ng wall. Dahil ito sa parehong direction ng movement ng contraction ng steel rod tsaka ng paglalapit ng walls. Again, inserting the formulas here, we have yung formula for temperature deformation. And equal ito sa pinag-add na yield tsaka yung deformation due to yung imaginary load natin. You cannot cancel out the length here. Be careful. And again, we will use the original length. Substituting these values, we find that the stress in the steel rod will be 53.6 megapascals, given that the walls spring together at 0.5 millimeters. Notice kung paano bumaba ang stress. Yun ay dahil pareho ng direction ng pag-yield ng wall sa contraction ng steel rod. Para sa isa pang example, let's have the second problem. A rigid bar of negligible weight is supported as shown in the figure. If the weight is equal to 80 kilonewtons, compute the temperature change that will cause the stress in the steel rod to be 55 megapascals. Assume that the coefficients of linear expansion are 11.7 micrometers over meter times degree Celsius for steel and 18.9 micrometers per meter times degree Celsius for bronze. Okay, intindihin ulit natin yung tanong. Anong amount daw ng change in temperature ang kailangan para ang final stress ng steel rod ay 55 megapascals? Final stress, ha? So first step at importante ito ay ang mag-draw ng free body diagram. Set your labels which force is which para malinaw din ang ating equations. May downward force, so probably supports ito and upward forces. Kapag na-encounter na natin ang ganitong system wherein the force loads ay may certain distances, hindi enough ang summation of forces in a y direction. We also need to acknowledge that there must be net zero moment para in equilibrium lang ang rigid bar na ito, or there will be no movement sa rigid bar. So if we find the summation of moments at point A, we have 1 meter of moment arm to force in steel plus 4 meters away to the force in the bronze. Then, since downward direction ito at negative sign, dito natin ilagay sa right side of equation. It is 2.5 meters away having a weight of 80,000 newtons. Yan ang force distribution ng weight alone. Pero ito na rin ang pwede natin gamitin to find the stress sa bronze. Using P is equal to stress times area, ito ang equation. Substitute natin ang final stress ng rod which is 55 megapascals. Ang area nito, pati ang area na rin ng bronze, we will find na ang stress in bronze is 35.08 megapascals. Tandaan natin na final stresses na ito. So ito ang gagamitin natin para mahanap ang change in temperature na nag-cause nito. Like we always do, imagine na mag-deform ang steel rod and bronze relative sa effect ng load at ng change in temperature. It has to be this shape. From this position, maaaring bumaba. Then the amount of deformation sa rod supports corresponds as this. May mga similar triangles, ano? So, the total deformation in steel rod is temperature deformation plus the deformation due to load. Ganun din sa bronze rod. These two are similar triangles, so they can relate in proportion. We have total deformation in steel over 1 meter equals the total deformation in bronze over 4 meters. We can then insert the formulas. Dapat ang missing value lang natin dito is the change in temperature na common sa both bronze and steel. Using this sa ating ratio proportion kanina, then inserting yung given data natin, we will find that the change in temperature is equal to negative 28.3 degrees Celsius. Negative sign indicates that there is temperature drop, which tends to shorten the steel and the bronze. Ibig sabihin, binawasan ito ang initial tensile stress, dulot ng weight. Anyways, you can always get back to the question and solve it on your own para mas maintindihan. You can solve it on your own ways kahit gaano ka-efficient basta accurate din. For other problems regarding thermal stresses and deformation, narito pa ang ilan with answers.